early corporate technology architectures collapsed under the sheer mass of their own deterministic engineering, exposing a fundamental design flaw within the historical foundation of early enterprise artificial intelligence frameworks. Before the global emergence of modern machine learning topologies, enterprise operations relied exclusively on symbolic artificial intelligence, translating valuable human domain knowledge directly into rigid, deeply nested conditional statements. These massive historical implementations came to be known as enterprise expert systems, operating as hard-coded rule engines designed to execute complex logical operations based on strict, predefined procedural paths. Every critical corporate business process, compliance policy, and back-end operational workflow had to be explicitly declared by core software engineering teams as an unyielding sequence of nested conditional arguments. As global organizations rapidly expanded their legacy digital footprint, these fragile networks of hard-coded statements scaled poorly, creating an acute architectural crisis that completely gridlocked mission-critical software environments. Data analytics from the Elsevier Journal of Systems and Software repository confirm that structural code complexity limits are quickly exceeded when deterministic models try to map highly variable environments. Whenever unexpected operational variables suddenly occurred across corporate production networks, traditional database lookups experienced severe execution latency, resulting in widespread systemic software crashes due to completely unyielding rules. Every new operational exception required a manual software update, which increased code coupling and transformed enterprise software into an unmanageable web of conflicting logical paths and technical debt. According to official research from the ACM Digital Library Software Architecture, this pattern of continuous architectural decay introduces profound vulnerabilities and massive operational risks into distributed corporate ecosystems. The problematic interweaving of hard-coded domain data directly with core conditional execution routines created a massive structural bottleneck that completely restricted dynamic runtime scalability across all corporate technology stacks. When system rules expanded into the tens of thousands, parsing the entire codebase sequentially for a single validation query forced processing nodes to consume unsustainable cycles of computational overhead. This lack of complete decoupling meant that modifying a single operational statement threatened to break distant, seemingly unrelated application segments, resulting in catastrophic downtime across enterprise resource networks. To successfully survive this systemic structural fragility, enterprise architects initiated a profound paradigm shift, separating business logic rules from database layers to construct a highly modular software pattern. This innovative structural split led directly to the modern development of autonomous inference engines, which operated completely independently from the underlying factual repositories containing static enterprise business data matrices. Under this specific architectural blueprint, the expert system was explicitly partitioned into two core functional components: the rule base, containing corporate logic, and the separate dynamic execution engine. The rule base functioned strictly as a declarative knowledge repository, while the decoupled inference engine applied logical frameworks to determine how these rules should evaluate incoming operational facts. As outlined in technical references from the Cambridge University Press Computer Science Registry, separating logic from data represents a foundational shift in automated logical inference processing design patterns. This structural separation resolved the problem of hard-coded dependency chains, allowing enterprise software engineers to alter specific business rules without modifying the underlying processing code of the runtime engine. Inference engines achieved this superior efficiency by executing rules through two primary processing modalities: forward chaining, which is data-driven, and backward chaining, which is entirely goal-driven in nature. Forward chaining began with the ingestion of raw available data, processing it through the rule matrix to systematically discover and assert new logical conclusions across the business domain. Conversely, backward chaining started with a desired objective or hypothetical conclusion, working backward through the conditional paths to verify whether the supporting foundational data actually existed within databases. To optimize this intense computational evaluation path, architects implemented the famous RETI algorithm, a highly specialized pattern matching routine that completely revolutionized rule execution speeds in corporate expert systems. The RETI algorithm constructed a directed acyclic graph of rule conditions, effectively bypassing the need to iterate through every single rule statement whenever data states changed in the repository. By evaluating changes across network memory tokens rather than rebuilding the rule evaluation path from scratch, the algorithm achieved remarkable sub-second validation execution speeds across dense production configurations. This structural transition from raw hard-coded code bases to decoupled inference networks profoundly modified the total cost of ownership profiles and core labor market dependencies for major global enterprises. Development overhead shifted dramatically from continuous, low-level dynamic software engineering activities straight toward manual, highly meticulous data curation and rule mapping validation routines systematically performed by human domain analysts. This sudden operational evolution gave birth to the early corporate engineering specialty known as knowledge engineering, where dedicated professionals systematically mapped human expertise into machine-readable symbolic logical constraints. Statistical metrics gathered by the International Labor Organization Future of Work Index highlight how these structural changes generated early roles in corporate code compliance, auditing, and verification markets. Instead of writing raw procedural software code, these specialized compliance experts spent thousands of hours gathering domain rules from human masters and coding them into formal symbolic structures. While this separation lowered initial software development costs, it created an unforeseen maintenance cycle where rules had to be continuously audited to prevent structural conflicts within data models. The total cost of ownership shifted directly from traditional runtime software debugging to massive, labor-intensive data curation efforts, revealing that early rule-based systems were not completely self-sustaining corporate assets. Corporate deployment life cycles demonstrated that as a symbolic system's rule base grew linearly, the combinations of potential logical interactions among rules expanded exponentially, creating unpredictable software edge cases. To deploy these deterministic software architectures securely, modern technology executives must establish explicit roadmap methodologies that carefully map out internal logic paths into isolated, highly modular rule segments. By segmenting the global rule directory into independent domain sections, engineering teams can minimize unintended rules crossover and completely eliminate the processing bottlenecks associated with oversized RETI graphs. Furthermore, regular automated software compliance scans must be executed to identify dead logic loops, orphan parameters, and contradictory conditions that degrade the runtime performance of active inference systems. However, technical history proves that deterministic symbolic trees are fundamentally limited because they cannot adapt organically to ambiguous corporate data environments or highly variable real-world operational scenarios. When confronted with noisy, incomplete, or heavily corrupted dataset inputs, traditional enterprise expert systems experience total operational failure, lacking the statistical flexibility needed to perform approximate logical matching. To bridge this gap, modern system architectures must transition from entirely deterministic symbolic structures toward flexible, probabilistic machine learning models that excel at pattern recognition across large scales. Probabilistic architectures use continuous mathematical vector weights rather than static binary rules, allowing enterprise applications to calculate confidence intervals and make intelligent data-driven decisions under operational uncertainty. As documented in research from the Carnegie Mellon University AI repository, mapping structural model failure vectors shows how rigid logical constraints can be mitigated by introducing probabilistic systems. This massive algorithmic evolution does not mean symbolic logic should be entirely discarded. Instead, the modern technology industry is entering the era of unified neuro-symbolic artificial intelligence architectures. Neuro-symbolic computing actively merges the sensory perception and pattern recognition capabilities of neural networks directly with the absolute mathematical precision and auditability of traditional symbolic expert rule engines. Advanced research frameworks from the MIT Computer Science and Artificial Intelligence Lab emphasize how neuro-symbolic logic engines optimize sparse computing architectures and eliminate the reasoning flaws of large neural networks. By combining these two approaches, enterprise systems can use deep neural layers to parse unstructured incoming data formats while using a symbolic rule set to strictly enforce security boundaries. This hybrid architecture guarantees absolute deterministic compliance for sensitive corporate operations, such as financial transactions and medical diagnostics, while maintaining the flexible capability to process complex, high-dimensional inputs. Furthermore, the strategic inclusion of a symbolic validation layer effectively eliminates the problem of model hallucinations, which continues to plague generative large language models within enterprise production environments. Enterprise technology frameworks are utilizing these neuro-symbolic patterns to rebuild legacy automated rule bases, converting thousands of hard-coded code lines into elegant, dynamic, and highly verifiable decision matrices. As technology stacks evolve, understanding the architectural shift from hard-coded conditional systems to modern probabilistic hybrid infrastructures becomes crucial for maintaining structural integrity and corporate digital transformation success. By reviewing historical engineering choices, current software development leaders can identify clear warning signals of technical debt, such as tightly coupled modules and excessive lookup execution performance degradation metrics. Modern technical frameworks that successfully combine symbolic rules with vector representations offer the optimal blueprint for building robust, scalable, and secure artificial intelligence systems for global business environments. Architects must carefully evaluate their internal operational data structures, determining whether their existing business validation rules require absolute binary certainty or can thrive under continuous statistical confidence metrics. If absolute security compliance or strict regulatory auditable tracking is required, keeping a separate declarative rule layer remains an irreplaceable dependency that machine learning weights cannot independently fulfill. Conversely, if the core corporate goal involves processing fuzzy text, unformatted audio data, or highly complex real-world vision feeds, neural infrastructure elements must take lead execution authority. Navigating this balance is the core tech challenge of our generation, demanding that enterprise software engineers master both classical symbolic rules and advanced neural network design architectures simultaneously. By avoiding artificial industry hype and focusing strictly on verified computing engineering principles, organizations can construct robust software ecosystems that completely withstand the test of temporal technical debt accumulation. The foundational lessons of the early symbolic artificial intelligence era serve as an enduring reminder that hard-coded rules alone cannot build autonomous enterprise intelligence without probabilistic flexibility frameworks. As you analyze your internal corporate technology infrastructure roadmap, prioritize decoupling business logic rules from core application engines to establish an agile development footprint ready for neuro-symbolic modernization. Empirical industry data demonstrates that modularity remains the ultimate defense strategy against software decay, providing the scalability necessary to maintain a distinct competitive advantage within dynamic global markets. Prepare your systems today for the hybrid neuro-symbolic intelligence models of tomorrow, ensuring your code base remains auditable, mathematically precise, highly performant, and structurally immune to operational failure vectors. Stop guessing your tech strategy and wasting your time. Subscribe to Enterprise Tech Brief right now. We deliver zero hype, pure architecture, the blueprint of enterprise intelligence, completely free. Hit the subscribe button